My name is Peter Gorm Larsen. I am a professor at the Department of Engineering at Aarhus University. In this small slidecast, I'd like to present to you how you can make software specification using the VDM SL, VDM specification language notation, and I hope that you will enjoy it. In my agenda, I have two parts. I'll first give you an overview of VDM briefly, and then afterwards I'll try to show you what the process is recommended for writing a formal specification using a small alarm example that originates from a real industrial case. So with respect to VDM, from a background perspective, our goal in the way we're developing this further is that it should be well-founded but also accessible in terms of being able to do modeling and analysis. We have made a series of tools. Started off with VDM tools that was developed at a company called IFAT that I used to work for many years ago. When I left that, we created an open source new opening called Overture. Later on, in a project called Destex, we developed that further in something called Crescendo, which enabled us to combine it with models of systems that could describe the physical behavior of a physical system, cyber-physical system, for example. This was taken further on in a tool called Symphony that was essentially meant to support system of systems. And finally, most recently, we've been taking it forward into a tool chain called IntroCPS that came from the IntroCPS project supported by the Horizon 2020 program that I was coordinating. Essentially, if you look at the ideas we have, is it's kind of trying to do pragmatic development methodologies where there are industrial applications. The thing I'm mostly proud of is that 250 million mobile phones in Japan is using VDM or something that has been developed using VDM inside the near-field communication chip that is doing payment in virtually all transactions in Japan. So VDM as such is a model-oriented specification language. It has been extended with objects in real time in different dialects. There are basic tools for supporting static analysis. There's a strong support for doing different kinds of simulation and testing. And then there is model-based test things using JUnit-like principles. And essentially, that is all what we have. The VDM Vienna development method originally was developed at a part of IBM Precision in Vienna back in the 70s. There are now three flavors. There's the VDM SL, VDM specification language, which I'll mainly be talking about in this presentation. That has been turned into an ISO standard many years ago. But an object-oriented extension of that, introducing classes, inheritance, and concurrency, have been put into a tool or language called VDM++. In addition to that, there's VDM RT, VDM real-time, that has real-time and distributed features. So you can both have a notion of time that progresses while a model is being analyzed, as well as you have deployment to separate CPUs. The fun I'll be focusing on in the presentation here is purely the specification language. And if you look at the specification language, it's model-oriented. It means that we have simple abstract data types. We have invariants that can restrict the memberships that we would like to have for our types. We have two ways of specifying behavior, either implicit style, pre-post, so what should hold before some operation or function, and what should hold afterwards. And then we have explicit style, where we kind of, either in a functional manner or in an imperative manner, is able to describe how you calculate the results from the inputs. So different books have been made by, in particular, John Fitzgerald and myself. VDM SL has a concept of modules where you have imports and exports, and the different kinds of definitions we can have inside each module include state, types, values, functions, and operations. In the presentation here, I'll primarily be talking about functions and types, and values are very easy constants that you could define. State I'll not touch upon, but it's the usual way you would have state in an imperative programming language, and that can be touched upon by operations. In a VDM++ setting, we have also written a book back in 2005, and there's a Japanese translation of this one as well. And here we have a notion of classes, we have inheritance, multiple inheritance. State here is called instance variables. The kind of definitions are otherwise the same, except that there is a way of doing threading, so having concurrency described. And these are synchronized by something called permission predicates, so essentially logic. And there's also, at this point of time, also a notion of traces that's being used for test automation support for combinatorial testing that is being talked about in a different presentation. So if we look at it, the data types perspective, there are a number of basic types and there are some compound types. In the basic types, Booleans, which you have in virtually all programming languages, are essentially having the true and false, and you can write it like this. The colon equal sign indicates assignment to an instance of something called flag. Numeric types are different of, and they're just subtypes of each other. We have nat1 starting from 1 and upwards, natural numbers that start from 0, integer, and we have reals. There's a special type called token, and token is a way of abstracting away from the exact representation you would like to make in your implementation later on. The only thing you can do with tokens is you can compare them and see if they're equal or unequal. There's also a notion of quote types. Essentially, it's similar to what you see as enumerated types in any programming language. Here, in this case, we have red and blue, just with these smaller than and greater than signs around it. And we have a number of characters. So characters can be put together to be forming a sequence of characters. And then you have a string like Peter here. From a compound type perspective, we have a notion of sets. I will come back to sets in a minute, but here you see an example of a set called S. It's assigned to the set of 1, 3, 5, and 8. And then there is a membership question whether 1 belongs to the set S, and that's true. If we look at sequences where there is an ordering, then we have a sequence here with 5 different elements. And if we look up the fourth of them, because we start numbering from 1, we get 8 coming out. We have a notion of mappings, and mappings are essentially finite functions. In this case, it goes from integers to reals, and we look up for a particular value in the domain and get the corresponding range value. For product types, they are written with stars in between them, and values of such product types are identified by means of a make mk underscore and then brackets around the actual elements. When we have these kind of product types, we can also select a particular field from it. So in the x.numbership1, we're selecting the first field. Essentially, that would be 1 in the one we have above it. We have record types, which is a more elegant way of having these represented. Here we have a pair, where A is the selector for the first element of the pair, and B is the selector for the second element of the pair. And it looks very similar to the other one, except that the values now have a name of the record it's defined from as a part of the value. So mk underscore pair is essentially a way of indicating that this is actually a value coming from the pair type. And we can then use the selectors like A in here. There's a notion of union types, where you can say either they belong to one type or another type or another type. So in this case, we have like an enumerated red, green, blue, and then the color, for example, could be assigned to a red color. For this, finally, there's a type notion of optional types, and it's written with these square brackets around a type name. Essentially, it's equivalent to kind of just adding an extra nil value, similar to what you can have in object-oriented programming with a null value. If we move on to data invariance, essentially it's a way of trying to take a type like dt here and then restrict it to only be the values that satisfy a particular invariant for that dt type. So in case we wanted to represent all the even numbers, we could make an invariant saying, well, the even numbers only where n mod 2 is equal to 0 will be considered. So the inv is a keyword, and then the n is representative of the value on the right-hand side of the equal sign of the nat, and then the equal I'm saying is defined as, so the invariant is defined to be. If, for example, we wanted to make another kind of invariant where we had a pair of values, like one natural number and one real number, but we wanted to represent the fact that the first one is smallest, then we could write it like this. Here, that the thing we have after the inv is actually a pattern. And that's because you can do pattern matching in the same way as you can in any functional programming language, anywhere where you can have an identifier. So in this list of parameters, we essentially are saying that n and r are the first element is called n, second element is called r, and then n smaller than r essentially is the predicate we would like to have. If we, for example, had sets of sets and wanted to describe the invariant that they are going to be disjoint, we could do it like this, because it corresponds to saying that for all sets S1 and S2 in the set SS, which is the set of the sets, it must hold that in case the two sets are different, then the intersection of them must be equal to 0, or the empty set. So if we look at sets in general, it's unordered collections of elements. There's one copy of each element counting, so to speak. The elements themselves can be of any type, so we have sets of sets, just like we saw before. So it's written with, from a type perspective, like set of int, for example, and we could have a value looking like this. It has 4 elements, or the empty set, which is written like this, which have 0 elements. For each of these different collection operators, we have a number of basic operators that are built into the language. Here we have the operators for sets. And what you see in the left-hand side column here is the ASCII syntax that you would type in a tool like Overture, which Overture is an open source tool for VDM support. Or you could kind of look at the mathematical symbols for the same things, which is corresponding to what you would typically see in the math books. And the last column here is indicating the signature of the operator. So in a membership that we saw earlier, E in set S1 is essentially taking something of type A and something of type set of A, and it's giving us a boolean coming back. That's the way to read these tables, and these operators are really important to learn and how to use them and combine them. Now for sequences, we can also call them lists. They don't have fixed length array length like in Java arrays. They are ordered collections of elements, and they're numbered from 1, not like 0 like in Java or in C. Accessing an element is done by normal brackets, not by square brackets. So list of 1 would be the first of an element, this first element of a list. Multiple copies are allowed, and they count. The elements themselves can be of any type. So we could have sequence of sequences. So we could either have sec of int, for example, or sec1 of int, which means it's a non-empty sequence that we are interested in. Elements could look like this. So here we have a list that has a length 5, or an empty one which we've written like that. Again, we have a number of built-in operators. Here's the list of the operators that we have for sequences. This is a common way that you would operate with these. If we move to mappings, last of these collection types, it's an unordered collection of pairs, maplets, but they have a unique relationship. So it's like a finite function mapping keys to values. It's like Python dictionary, in case you know Python. The elements themselves can be of any type. So for example, we could have a mapping from integer to real. It could look something like this. So here we have 3 different elements mapping to 3 values. Note that 1 is mapping to 3 and 5 is also mapping to 3. That's perfectly all right, unless we like to have an injective mapping. An empty mapping is written like this. in order to distinguish it from an empty set. So here we have the operators for mappings, and they are some of these are used a lot, and some of those are used a little bit less frequently. The injective mappings you see here in the inverse of a mapping that is required to be injective. When you want to specify behavior, it can be done in terms of postconditions, like a contract. So if you want to take a square root of some number and getting some number back, essentially it's the same as the number that multiplied by itself. This is an implicit style. We cannot execute that in a tool like Overture. Alternatively, one can write an explicit version, and here we can see also there's a math library that one can import, and that would have a square root function, so it's a little bit cheating, you can say. But that's an explicit definition that can be executed. You can also combine these, so you can have pre and post conditions for such explicit definitions. And the post condition, you have the possibility of using a keyword called result. Result is then the thing coming out of the execution. So that's like a contract that should hold when you are completing your definition. So you can say the precondition is the caller's responsibility, the post condition is the guy who is making the behavior's functionality. That's his responsibility. So I hope that gave you a quick overview of VDM. And now I'll try to show the process we recommend for writing such a formal specification using a small alarm example. And the steps that are important here is, first of all, to determine what's the purpose of the model. The purpose is used to kind of determine what things can you actually abstract away from, what do you need to incorporate in the model, and what can you leave out. Then you read some requirements, and we assume these have been written down. Of course, in many cases they are not. And then you can use this to try to guide the production, the definition of such requirements. But from the requirements, we can try to extract a list of possible data types. Typically, these are nouns in the text, and operations or functions, typically from the actions in the text. And then create like a dictionary, kind of giving explanatory names to the things in this list. Then you can sketch out representation for the types that we would like to use in the model. And sketch out what I call signatures for the functions and operations. The difference between a function and operation is that a function cannot see a state. It cannot touch it at all, whereas an operation can see a state and also manipulate on the state unless it's a pure operation. Again, these signatures are indicating what input types would we like to take, what output results do we get. And then we can check the consistency of the model we have produced so far, for example, using Overture. Now, once this is done, we can kind of try to complete the data type definition and potentially adding invariants from the requirements and then trying to formalize such invariants. You're going to see that in a moment when I'm trying to do it for this small alarm example. Now, next step here is trying to complete the operation definitions or function definitions, determining pre and post conditions. So the different steps for developing a formal model starts off by determining the purpose of the model. The purpose is important to determine what things you can actually abstract away. Then you need to read requirements. I'm now assuming that you have the requirements written down. Otherwise, I have in industry tried to use this to drive the production of the actual requirements. From such a requirement list, you can actually try to extract different possible data types, typically from the nouns, and functionality, operations and functions, often from the actions. And then we can create a dictionary giving explanations to the items in this list. Now, next step would be to sketch out representations for the types, and then sketch out what I call signatures for the functions operations. Again, you can check the consistency of these using the Overture tool. Now, signatures are essentially the types that the functions and operations takes as input and gives as results. Now, then we can complete the type definitions, determining potentially invariant properties from the requirements and then formalizing these. Next step would be to complete the function and operation definitions, determining pre and post conditions and the operation bodies, modifying the type definitions if necessary. And then you would go and validate the specification using systematic testing and potentially rapid prototyping. So essentially, this is the process. Eventually, you would implement the model either using automatic code generation or manual coding, but I'm not going to go into that in this presentation. So we use a small chemical plant as an example for this. And imagine you have alarms coming into a controller that needs to call upon experts that can deal with different alarms. But these different alarms can come from different areas and different application domains, so it may be different experts that needs to be called upon duty. So whatever we are calling here, there are different experts that needs to be put into the contract. The requirements are on purposely made such that it fits a one page. This is inspired from a real case study, a real piece of industrial development, but cut down so nobody can see where it actually comes from. So if I just try to read these 8 requirements that we have here, the first one is to have a computer-based system that is to be developed to manage the alarms of this plant. There are 4 kinds of qualifications that are needed to cope with the alarms: electrical, mechanical, biological, and chemical. There must be experts on duty during all periods allocated to the system, and each expert can have a list of qualifications. Each alarm reported to the system has a qualification associated with it, along with a description of the alarm that can be understood by the expert. Whenever an alarm is raised by the system, an expert with the right qualification should be found, so he or she can be paged. The expert should be able to use the system database to check when they will be on duty, and finally it must be possible to assess the number of experts on duty. You may consider to pause the video here and try to consider yourself, before you continue, what would be the key questions that you would go and ask the person that's responsible for the requirements list here before you would go ahead and try to develop this. So I'll move on and say the purpose of the VDM SL model is essentially trying to clarify the rules that govern the duty roster and the calling out of experts to deal with the alarm. So I'll use this to determine what I can abstract away in my analysis and what I need to include. So if I try to create a dictionary, the potential nouns that I found here are an alarm, required qualification, description. We have a plant, which is the entire system. That is something that you typically do not have and not represent when you just try to implement things, because that would be the entire system. But when you need to make a formal model of it, it may be very convenient to model the entire system as well, in order to be able to document potentially invariant properties with it. Then we have a notion of a qualification: electrical, mechanical, biological, and chemical. We have an expert that has a list of qualifications. We have a period. Whatever shift period system is being used at this plant, we don't know. That hasn't been documented to us. And then finally, there's something about system and system database, so probably some kind of schedule. The potential operations and functions that needs to be taken care of include an expert to page. So when an alarm appears, what's involved? We need to find, we have an alarm operator, we have a system, and we need to find someone who can deal with it. Expert is on duty. It's a matter of checking when you are on duty. We need to consider what's involved. It's probably an expert and a system that needs to be interacted with in order to find out if I'm going to be on duty at a particular time, and then number of experts on duty. Presumably, it's for a given period. What's involved is probably the operator and some kind of system. So that would be my dictionary. Now, sketching out type representations, requirement 2 said we needed 4 qualifications. Well, for something like this, it is very appropriate to simply use an enumerated type, because these are the ones we know that we need to deal with, and essentially it's just having these 4 possibilities. Now, this union operator there, this bar, is kind of giving us the union of each of these quote literals. The individual quote values are put in these angle brackets with a bit of text in between them. And this type then has 4 elements corresponding to our 4 kinds of alarm and qualification. It's just like enumerated type in a programming language. So if we now move to R5, which said each alarm has a description, so a text for the expert and a qualification. Now it's worth asking the customer, the user, if the client really means A, or some, or at least one. Each alarm has a qualification and a qualification. Could you have more than one? Let's just assume that our client have told us that I need exactly one. And then I would do something like this. I would make a record where I have an alarm text, that would be my sequence of character, and I have a qualification and only one qualification. So that would be a way of doing this. Now, a record type like this alarm means that we have a value of this type T, so we can write V:T. Then, so if we want to state that A is an alarm, we write A:"alarm. And in order to extract the fields from a record, we would use the selector alarm text. We use a dot notation, so A.alarm text would give us an alarm. So in case we had A being made up some value, we would use a record constructor, this MK underscore, and then the type name, which is alarm, so make alarm, and then the text could be disaster, get here fast, and then the electrical guy would be there. That could be one that we would like to do, and then alarm text would be the disaster, get here fast. This kind of make underscore alarm is like a constructor. It's building a record from the values of its fields. If we continue, then alarm requirement R4 said that each expert can have a whole list of qualifications, not just one. We have to ask the client, do you really mean a list? Is there an order in which he's primarily an electrician, secondarily he is a mechanical guy, or do we say that it doesn't matter the order there? So I have assumed here that he says it doesn't matter, and then I would model it using a set representation, set of qualification. So we have some ID for the expert, and then we're going to have a set of qualification. So sometimes requirements given in natural language do not mean exactly what they say. So if in doubt, consult an authority or the client, and hence, in here, I have modeled as a set rather than as a sequence. So we try to keep the form specification as abstract as possible. So we only record the information that is needed for the purpose of the model. The choice of what is relevant and what is not relevant is a matter of serious engineering judgment, especially where safety is concerned. Now, when we want to sketch type representations, we can also use this special type called token. Token is something we would use where the informal requirement doesn't tell us how the identifiers should be. So we want to leave freedom to whoever is going to implement it at some stage. So here we could say expert ID, I'll define it to be a token. And in the same spirit, it's also true for the periods in which the plant's timetable is split. These periods, we don't care how big these periods are, how they're identified, we just call them token. Now, sketching the type representation also means that for R3 and R7, we need to consider what to do. There must be experts on duty at all times, and it should be possible to check if a given expert is available. So these requirements imply that there must be some sort of schedule related to each period of time of the set of experts who should be on duty in that period. So I have modeled it like this. So the schedule is a map from period to a set of experts. So it means that there must be experts on duty at all times. So that means that we have a mapping from the period and then to the experts that are on duty at that point of time. So it could look like this. Let's say we had a two turn shifts, one for the morning, one for the afternoon. Then for Monday morning it could be E1, E7, and for Tuesday afternoon it could be these three experts, and the same would hold for Monday afternoon. So they would come both afternoons, but some other people would be there on Monday and Tuesday morning. So when we sketch out these type representations for the entire plant R1, the computer-based system should be able to manage an expert call out in response to alarms. I think I both need a schedule and I need a set of alarms that could appear in my plant. So far, the type definitions we have made includes from the top, the plant should have a schedule and a set of alarms. The schedule should be a map from period to set of experts. And then a period should just be a token. An expert should have an expert ID and a set of qualifications. And then an expert ID is again a token. The qualification is this kind of enumerated type. And the alarm is a record with alarm text and one qualification. So far, so good. Let's try to sketch some function signatures. The possible functions were expert to page, expert is on duty, and number of experts. So the function definition shows the types of the input parameters and result of the signature. So if I say expert to page, I say we need an alarm, we need to know what period this is appearing, and we need to have a plant. And given all of this, we'd like to find an expert to page. So that should be an expert we're coming out with. Expert is on duty. Well, we need an expert and we need a plant in order to get the set of the periods where the expert is on duty, typically written out in some order. So we would have to consult our client to see if they wanted a particular order here. Finally, the number of experts. We need a period again, and we need a plant, and then it should give us a natural number about how many people are going to be on duty in this period. So then the recommendation was we should try to complete our type definition. So adding potential data type invariants. So for example, that suppose we agree that the client should always have at least one qualification. This is a restriction on the expert type. To state this expert, we would do it like this. We would say the expert quality should be different from an empty set. You could find places in corrupt countries where that would not be put in, but certainly it would make a lot of sense to do that in civilized countries. So we attach such an invariant to the definition of the relevant type. So here in the expert, where we have that expert has a set of qualifications, we need to say that the invariant that EX, that's the formal parameter standing for the typical element of the type, and then the body of the invariant is the Boolean expression containing the restriction using the formal parameters that we have there. And here we make use of the selector called quali, because ex.quali should be non-empty. Now, there also was a requirement that there must be experts on duty at all times. This is actually a restriction on the schedule to make sure that for all periods, the experts are not empty. Again, we can state it formally and consider that we have a typical schedule, call it SCH. We would need to do something like this. We would say for all sets of experts, call them EXS, in the set in the range of the schedule, it must be such that the EXS is different from an empty set. At least one expert must be on duty. So if we want to attach this to the relevant type definition, we get this. So after schedule, we write this inv SCH and then say for all EXS in set range of SCH, it should hold that EXS is different from the empty set. Actually, we can do that more smart, but we'll see that later. When we complete the function definitions, then when we have a function signature like this, we need to have a parameter list. So that means that we give names to the different arguments we have for our function. I call period for peri and plan for PL in this case. And then a body, in this case, where we number of experts, we need to take the size of a set. So we look up with the given periods in the schedule from the plant, and then we say what's the size of it. And here we need to have a precondition because the period needs to be one of those periods that actually is defined in our schedule in the plants. So if we omit a precondition, it's assumed that it's true. So then it can be always be giving the version of the right type. Now it's the call's responsibility to ensure that actually you're calling it with a period that is one of the defined periods. And then we need to complete the function definitions again also where it needs to be possible to check if a given expert is available. Now here I'm using something called a set comprehension. At first this may look peculiar to you, but once you get used to it, you will see that it is really powerful kind of construct. The way to read this is that we want to say that peri is in the set of the schedule. So we run over all possible periods, and if the property that's written after this ampersand is true, so EX is in the set of the period, meaning he's on duty, he's one of those who is on duty, then we want to take the period out because we're interested in, for a particular expert, finding out what are the set of periods where he's on duty. For convenience, we can actually use a record constructor in the input parameter as well. So it's called a record pattern. And it means that instead of writing PL here, we could write make plant schedule of alarms. And in fact, we don't even need to use the alarms. So we can just replace that with a don't care pattern. So it means that the final version of the function looks like this. And then we can make it simpler in the sense that we want to kind of say the schedule part of the alarm I called SCH, and then I only need the schedule here, and I don't need to look up as you saw before. We could have expressed some of the other invariants for the other definitions a little bit simpler as well, but you can do that as an exercise on your own. Now, completing the function definition also for this one. When an alarm is raised, the system should find the name of the qualified and available expert who can then be called in. Well, we have the type of it. I've given some names to the alarm, the period, and the plant. But how can we define this? Well, we can kind of specify what results should be returned without worrying about how to find it. We could use an implicit style definition. So we could say the property we are interested in is that the result, now here I use R to be able to refer to the results. The results should be in the set of the periods. If I look up in the schedule, then in the plant, that should be, the expert should be one of those who is on duty. But in addition, it should hold that the alarm, if we take the qualification of the alarm, it should be one of the qualifications that the expert is possessing. So this is exactly saying what we want, not how we want to find that particular person. But have you spotted a problem here? Well, the requirements were silent about ensuring that there is an expert with the right qualification available. After consulting with the client, it appears that to be necessary to ensure that there is always at least one expert with each kind of qualification available. So how could we record that in the model? Well, if we look at the plant, the top level spec, it looks like this. Well, I can write an invariant that kind of states something like that we have a schedule and an alarm, alarms inside my plant. Then for all the alarms, it needs to hold that for all the periods in the domain of the schedule, there need to be existing an expert who is on duty in this period, such that the expert has the the alarm qualifications are covered by the expert. So that this is exactly precisely saying with property that is essential, that needs to hold at all points of time, in particular if you wanted to allow people to shift from one to another, this is invariant and needs to be satisfied. So finally, if we review the requirements, R1 said that the system needs to manage the expert call-out system to response to alarm. Yes, we have done that. We have 4 qualifications. Yes, we have done that. The expert on duty at all times. Expert can have a list of qualifications. Here we restricted it to be set unordered. Each alarm has a description and qualification. And the output, the name of the qualified and available expert, well, that's where we spotted a particular flaw in the requirements. And then check if a given expert is available. And then finally assessing the number of experts on duty in a given period. So if we look at the weaknesses of the requirements, there have been silence about at least one suitable expert is available. That was the major flaw that we detected here. And then we have used identifiers for experts. That was implicit. We didn't need to do it, but we have done it because it makes it more clear what we're having. There was a use of list where really it should be an unordered collection. And then there was a silence that the experts without qualifications are useless. There was nothing written about that. And then a qualification essentially meant several qualifications. So these are the weaknesses that were spotted in this, going through this process. In trying out this for real, I have done the same thing in much more complex things many, many times. And I hope you will be able to do some of the same things in your work. So the summary of the process of developing a model depends crucially on the statement of the model's purpose. So please always remember to do that. VDM SL models are based around type definitions and functions. Abstraction is provided by basic data types and type constructors, and their availability to give implicit function definitions. We had these basic types. We've been going through type constructors, going through invariants, functions, operations I haven't touched much upon, but these ones can touch upon a state. So with that, I'd like to close this, and I hope that you will make fun of using this.